So the final unit in the topic is hybridization. And by the end of the unit, you should be able to know that a hybrid orbital results from a mixing of different types of atomic orbitals on the same atom. By the end of the unit, you should be explaining the formation of sp3, sp2, and sp hybrid orbitals in methane, ethene, and ethine, and identify and explain the relationships through Lewis electron structures, electron domains, molecular geometries, and types of hybridization. So it's hard to imagine what the tetrahedral, well, basically all the geometries that you would get arising from the atomic orbitals we recognize. And this is where atomic hybridization comes in, okay? So in terms of orbital hybridization, hybridization is the combination, the mixing of the different types of orbitals on an atom to produce new types of orbitals. And it's essentially a mathematical procedure. The most common hybrid orbitals are combinations of the s and p orbitals of an atom that then form the sigma bonds. And the number of orbitals mixed equals the number of hybrid orbitals produced. Not all orbitals in a level are hybridized, which we will look at later when we look at pi bonding. And all we have to do is count the number of sigma bonds to determine the hybridized orbitals. Okay, so these are the shapes of the orbitals that have been hybridized. So if you have an s orbital and a px orbital, you get that funky sp hybridization, which is linear. If you have an s orbital and a px and py orbital, okay, you end up with a trigonal planar sp2 hybridized orbital, which has those 120 degrees. And the final one is if you have an s orbital and the px, py, pz orbitals are hybridized with it, then you get a tetrahedral shape for your hybridized orbital with an associated bond angle of 109.5. So we're going to look at 3 different case studies to highlight the different types of hybrid orbital. Okay, so the first one is the sp orbital. So in the sp orbital, it can be observed in the compound of acetylene, which you will soon know as ethylene. Okay, that's kind of the more scientific IUPAC name. So in triple bonds, and acetylene is basically 2 sp orbitals. Okay, so the carbon atoms here are sp hybridized, and the sp orbitals overlap to form this sigma bond here. And then the 2 pairs of p orbitals also overlap to form the 2 pi bonds here. Okay. And then also the sp orbital of the carbon can overlap with the s orbital of the hydrogen to form the associated CH sigma bonds. For 3 sp2 orbitals, which is highlighted by the molecule formaldehyde, which you will become to know it as ethanal because it is an aldehyde, we have the 2 have an sp2 orbital. Okay, so both oxygen and carbon are sp2 hybridized. They overlap to form this sigma bond here, and the unhybridized p orbitals overlap in the normal pi fashion, okay, which is your other pi bond. And you then have the final example, which is your 4 sp3 orbitals around the carbon. So in a molecule like methane, which is shown on the left, the sp3 orbitals on the carbon, okay, this guy here, overlap to form sigma bonds with the corresponding s orbitals of hydrogen. Okay, and that's the tetrahedral shape of an sp3 orbital. So then let's look at the bonding in carbon dioxide. So you have pi bonds from the overlapping p orbitals, which are not hybridized, okay, they're seen there. And you also have carbon and oxygen, which are differently hybridized. So you've got the sp hybridization of this carbon here and oxygen here, and the sp2 hybridization of this oxygen here. Okay, so the carbon is sp hybridized. Okay, that's going to be your 2 sigma bonds here. You've got the associated pi bonds, and then the oxygen can also sp hybridize and sp2 hybridize, depending on which oxygen it is. One oxygen is sp2 hybridized and one oxygen is sp hybridized. So you can also use orbital diagrams to explain this. So let's consider beryllium. Okay, in the ground state, it would not be able to form bonds because there's no singly occupied orbitals, but the 1s and the 2s are full. Okay, because it's 1s, 2s, 2. Okay. But if it absorbs a bit of energy, then that paired electron can be promoted to the 2p orbital. Okay, therefore it can now form two sigma bonds. Sorry, one sigma bond because for the s and one pi bond for the p orbital. So one sigma bond, okay, it can form one sigma bond and one pi bond. And if we mix the s and p orbitals of the beryllium atom, it yields two degenerate orbitals that are hybrids of these two orbitals. So these sp hybrid orbitals have two lobes like a p orbital. One lobe, of course, is larger and more rounded, as this is the s orbital. Okay, these guys here, this is the s orbital here, this is the s orbital here. And the sp hybrid orbital is basically shown as this particular shape because we don't really worry about these smaller the smaller s orbitals in the sp hybridization. This explains the shapes because these two degenerate orbitals would align themselves in 180 degrees from each other to reduce the electron repulsion, and this is consistent with the observed geometry of beryllium compounds, which are indeed linear. Okay, so beryllium's in the center. You have the two sp orbitals, hybridized orbitals, forming sigma bonds here with the 2p orbitals of fluorine to give beryllium difluoride. So in terms of the orbital diagrams of BF2, when the hybrid orbitals of the orbital diagram of beryllium would look like this. Okay, so it basically goes from a 1s 2p empty to an sp hybridized atomic diagram. The sp orbitals are higher in energy than the 1s orbitals, but lower than the 2p orbitals. That kind of makes sense because it requires energy to promote the electron from the 1s into the sp hybridized orbital. And that would form two sigma bonds. In terms of BF3 hybridization, again, you've got boron having an electron configuration of 2s 2 2p1. You promote the electron. Okay, this guy gets promoted up to the 2p orbitals, so you end up with a 2s1 2p2, which can be hybridized to an sp2 orbital, which would promote a certain particular shape. Okay, you've got three bonds. Actually, you end up forming three degenerate sp2 orbitals as such, which gives you this trigonal planar shape, which forms sigma bonds. For CH4 hybridization, carbon, of course, starts off with being 2s2 2p2. You promote the paired up electron into the p orbital. Okay, therefore it becomes 2s1 2p3, which hybridizes into the sp3 orbital, which forms four sigma bonds, which you would see, of course, in methane. Okay, so that's why it's tetrahedral, because the sp3 orbitals of carbon will overlap with the s orbitals of hydrogen to form four sigma bonds. So let's look at the example of hydrogen cyanide. So in hydrogen cyanide, what you have is basically a carbon and nitrogen atom, and the carbon and nitrogen atoms, basically the two sp orbitals of carbon and nitrogen, okay, the sp hybridized orbitals overlap to form a sigma bond. Okay, there's your sigma bond, and then the non-hybridized p orbitals in the px and py direction overlap to form the corresponding two other pi bonds. And the lone pair of the nitrogen is going to be 180 degrees away from the bonded electrons of carbon, which can then form another sigma bond with the s orbital of hydrogen to form that CH bond. So looking at the hybridization of nitrogen and ammonia, you can basically look at the ground state electron atomic orbital configuration of nitrogen. You can, if you add some energy, promote one of the electrons. Okay, so you get an sp3 hybrid orbital, which now has this lone pair. Okay, and that means you've got a lone pair and 3 sigma bonds. The number of electron domains will tell you what hybridization there is. So if you have 4 electron domains, therefore you would have 4 sp3 hybridization, because this lone pair on the nitrogen adds up as one of the electron domains. Okay, so you'd end up with a tetrahedral shape with one of the electron domains being filled up with that non-bonding double pair of electrons. Okay, so if we look at the hybridization of oxygen and carbon dioxide, we look at the molecule already. The number of electron domains will tell you what the hybridization is. Okay, and pi bonds form from normal p orbitals. So we start off with the ground state of the oxygen, which is 1s, 2s2, 2p4, and then we get the hybridization and hybrid energy states. So 2s stays where it is. The sp2 hybridized orbital now has 2 lone pairs and 1 unpaired electron, which can form a sigma bond, and the p orbital ends up with just having 1 electron, which can form a pi bond, which is indeed what we see here on this particular oxygen. So there we have the unpaired electrons. Here we have the sp sigma bond and the pi bonds forming here. Okay. Oops, not that one. The pi bond forming here for that particular oxygen. And it will be different for the other oxygen. So as a final problem, I want you to analyze the sulfate molecule. And in terms of analysis, I want you to identify and explain the relationships between the Lewis electron dot structure, the electron domain, the molecular geometries, and the types of hybridization. So it's basically using all the ideas that we've learned in structure and bonding and incorporate that into an analysis of this particular molecule. So we're looking at the atomic orbitals, hybridization, also ideas around both stable Lewis diagram, formal charge, concepts like that. Okay, so that's your mission. Pause the video now. Think about that. It should be quite in depth, and you should get, hopefully at the end, something similar to this. Okay, great. That's the end of this particular topic.